Why does the world exist? Why are we here? Why is there something rather than nothing? Philosopher Arthur Schopenhauer once said, "Except for man, no creature is astonished at its own existence. For all others, it is self-evident, and they do not notice it." Ludwig Wittgenstein, arguably the greatest philosopher of the 20th century, was stunned that the world exists at all. In his Tractatus, he wrote, "The mystical thing is not how the world is, but that it exists." Physicist John Wheeler, Richard Feynman's mentor, once exclaimed, "I want to know why the quantum, why the universe, why existence?" Curiously, this most fundamental question was asked rather late. It was first clearly formulated in the late 17th century by the philosopher Gottfried Wilhelm Leibniz, quite the genius, by the way, who independently invented calculus alongside Newton. But for Leibniz, there was no mystery. The answer seemed obvious. The world exists because God created it out of absolute nothingness. Everything around us is creation, ex nihilo. God is so omnipotent, he doesn't need any raw materials. He shapes the world from pure nothing. Most people still think this way. For them, existence isn't a mystery. God plus nothingness equals the universe. That's their version of the theory of everything. But even if we accept this equation, a new problem arises. Why does God exist? One might imagine even God asking himself, "I am eternal and omnipotent, but where did I come from?" Some have suggested that God, bored of contemplating his own existence, created the world simply to entertain himself. Now, let's remove God from the equation. What remains? Empty space plus nothingness equals the universe. If you're a Buddhist, you can stop here, because, in essence, it turns out that nothingness equals the world, which means the world itself is nothing. To a Buddhist, the universe is a grand illusion, a vast cosmic void. We think there's abundance all around us, but that's only because we're enslaved by desire. When desire dissolves, we finally see reality for what it is: emptiness. And in that moment, we slip into the blissful state of nirvana, where life itself becomes enough to embrace death. But most of us aren't Buddhists. We're still haunted by the mystery of existence. So what should we put in the empty space of the equation? Perhaps science. Physics is our best guide to the nature of reality. It seems capable of uncovering the true structure of the universe. Since the late 1960s, physicists have proposed a bold, purely scientific explanation that the universe could have emerged from nothing as a quantum fluctuation of the vacuum. Stephen Hawking was one of the leading advocates of this view. In 2010, The Times published a headline that read, "Hawking, God didn't create the universe." The photo showed God looking terrifying and Hawking looking smug. It felt like a duel between faith and reason. But Hawking himself insisted otherwise. "I have nothing against God. My work is not about disproving him. I'm simply searching for a rational explanation for the universe." He once reflected on his own life, saying, "For centuries, it was believed that disabled people were cursed by God. Perhaps I have somehow displeased the one above. But I prefer to think that everything is explained by the laws of nature." Long before Hawking, there lived a philosopher named Aristarchus in the 3rd century BC. He was fascinated by lunar eclipses, a true scientific pioneer. Aristarchus had the courage to doubt the gods. He realized that eclipses weren't divine omens, but the result of Earth's shadow falling upon the moon. That single thought liberated his imagination. He pictured the geometry of the heavens, the dance between the sun, Earth, and moon, and reached an even bolder conclusion. The Earth is not the center of the universe. It revolves around the Sunday. And the stars? They aren't holes in the sky, but distant suns themselves. A breathtaking revelation for his time, almost unthinkable. But where did matter, energy, and space come from? Until the 20th century, no one knew. The answer came from perhaps the greatest scientist of all time, Albert Einstein. He realized something astonishing. Two of these ingredients, mass and energy, are actually the same thing, two sides of the same cosmic coin. His famous equation, E equals mc squared, tells us that mass can be seen as a form of energy and energy as a form of mass. That means we can reduce the recipe for the universe even further. Now, only two ingredients are needed, energy and space. But where did they come from? Scientists discovered that both space and energy spontaneously emerged at the very first moment of the Big Bang. Yet, that only pushes the question deeper. Where did the Big Bang itself come from? Did the universe truly emerge from nothing? Some believe this is precisely where God enters the picture, the Big Bang as the ultimate act of creation. But science offers another explanation. We now understand the natural phenomena that once terrified the Vikings and mystified ancient civilizations. And using the same laws of nature, we can ask whether God is even necessary. Stephen Hawking once put it beautifully. I grew up in England. The years after World War II were a time of austerity. We were told that everything had to be paid for. But after a lifetime of studying the laws of physics, I can say this: you can, in fact, get an entire universe for free. Yet the central mystery of the Big Bang remains. How could an enormous universe arise out of nothing? The secret lies in a strange and elegant phenomenon, the existence of negative energy. Imagine you want to build a hill on flat ground. To pile up the dirt, you have to dig a hole beside it. You create both a hill and a pit, a positive and a negative version of the same thing. Everything balances out. The same principle applies to the birth of the universe. The Big Bang produced a colossal amount of positive energy, the energy of matter, radiation, and motion. At the same time, it created an equal amount of negative energy. Together, they sum to zero. So where is all that negative energy hiding? The answer is profound. It's in space itself. As Hawking explained, I know this may sound hard to believe if you're not a mathematician, but it's true. The vast cosmic web, billions upon billions of galaxies with gravitational forces between them, acts as a giant storage tank for negative energy. The positive side of things, mass and energy, is the hill. The corresponding pit, the negative side, lies in space. But what does all this really mean? If the total energy of the universe adds up to zero, then perhaps no divine hand was ever required to create it. The universe, in that sense, is the perfect free lunch. Yet one haunting question remains. What started the whole process? What caused the spontaneous creation of the universe? In everyday life, things don't just pop into existence. You can't snap your fingers and make an apple appear. It has to grow slowly, naturally. But let's dive deeper into that apple, past its sugars and water molecules, down to its atoms, and further still to the subatomic realm, where reality begins to blur. Here, at the quantum level, the impossible becomes ordinary. Particles can appear out of nothing, merge, vanish, and reappear elsewhere, all perfectly in line with the laws of physics. As Stephen Hawking explained, since we know the early universe was once incredibly small, perhaps smaller than a proton, we arrive at a remarkable conclusion. The universe, with all its dizzying scale and complexity, could have simply burst into existence without violating any law of nature. From that moment, as a colossal amount of energy was released, space began to expand, becoming the reservoir for all the negative energy needed to balance the equation. Of course, this raises another fundamental question. Did God create the laws of quantum physics themselves, the very rules that allowed the Big Bang to happen? Hawking's response was direct yet respectful. I have no wish to offend those of faith, but in my view, science offers a far more compelling explanation than the idea of a divine creator. In everyday experience, everything seems to have a cause. It feels natural to assume the universe must have one too. But perhaps that intuition fails when we apply it to everything. Imagine a mountain stream. What causes it? Rain in the mountains. And what causes the rain? The sun evaporating water from the ocean. And what powers the sun? Nuclear fusion, hydrogen atoms fusing into helium, releasing light and heat. So far, so good. But then we ask, where did the hydrogen come from? And the answer leads us back to the Big Bang. Here lies the crucial insight. The laws of nature not only allow the universe to arise spontaneously, just as a proton might appear out of nothing, but they also do not forbid the possibility that the Big Bang itself had no cause at all. None. This explanation is rooted in Einstein's theories. Space and time are not separate. They are fundamentally interwoven. At the moment of the Big Bang, time itself began. Imagine a black hole, a collapsed star of immense mass, so dense that not even light can escape its gravity. Gravity doesn't just bend light, it bends time. A clock falling into a black hole would tick slower and slower. And if it could somehow survive that unimaginable gravity, so what then? Inside a black hole, the clocks stop. And they stop not because they're broken, but because inside a black hole, time itself ceases to exist. That's exactly what happened at the birth of the universe. The role of time at the moment of creation is the key to understanding how the universe could create itself. As we conceptually travel backward in time, approaching the Big Bang, the universe becomes smaller and smaller until it collapses into an infinitely dense point, a kind of cosmic black hole. And just as within any black hole, the laws of nature behave in peculiar, extreme ways. At that limit, time must stand still. We cannot go back before the Big Bang because there was no before. Time itself didn't exist. What we've discovered is something that has no cause, because there was no time in which a cause could exist. There was no moment for a creator to act, no time in which a creator could exist at all. People want answers to big questions like, why are we here? No one expects simple answers, so we're willing to look hard for them. But when people ask me if God created the universe, I say the question itself is meaningless. There was no time before the Big Bang, so God had no time to create it. It's like asking how to reach the edge of the Earth. The Earth is a sphere. It has no edge. Searching for one is pointless. This is, in my view, the simplest explanation for why there is no God. No one created the universe, and no one controls our destiny. Which leads me to a profound realization. There is probably no heaven and no afterlife. Belief in an afterlife, I think, is wishful thinking. There's no reliable evidence for it, and the idea fades under the light of what science reveals. We turn to dust when we die. But the fact that we live at all that we think, that we leave a mark, that we pass our genes to our children, has deep meaning. We have one life to appreciate the grand design of the universe, and for that, I am deeply grateful. In this video, we'll try to do exactly that, to appreciate the grand design of the universe. Alongside Stephen Hawking's writings, I've also drawn from several remarkable books on this subject. My favorite among them is A Universe from Nothing by physicist and author of over 300 scientific papers, Lawrence Krauss, the book that most inspired this video. Hamlet once said, "I could be bounded in a nutshell and count myself a king of infinite space." He meant something profound. We humans are small, fragile, and limited in body, but our minds are boundless. They can roam the universe freely, asking the deepest questions imaginable, and sometimes even daring to answer them. Is the universe truly infinite? Did it have a beginning? Will it last forever? How can our finite minds ever hope to comprehend something without limits? And yet, we must try. Even if it means repeating the fate of Prometheus, who stole fire from the gods to bring light to humankind. For that act, he was chained to a rock for eternity. But one day, Hercules freed him. In the same way, our search for cosmic truth might seem like defiance, but it is also liberation. We have already made extraordinary progress in understanding the universe. Our picture is still incomplete, but physicists like Stephen Hawking believed we won't have to wait much longer. The Boshongo people of Central Africa have their own creation story. In the beginning, there was nothing, only darkness, water, and the great god Boomba. One day, Boomba felt a terrible pain in his stomach. He strained and vomited the sunday. The sun's heat evaporated the waters, and land appeared. Still in pain, Boomba vomited the moon and the stars, and then the animals, a leopard, a crocodile, a turtle, and finally, humankind. Like many creation myths, it tries to answer the same questions we still ask. Why are we here? Where did we come from? The answers often suggest that humanity appeared only recently, and perhaps that makes sense. We are still evolving, still learning, still climbing toward understanding. If we had existed forever, our progress would surely be far greater. In the 17th century, Bishop James Ussher even calculated the exact date of creation. According to his estimate, time itself began at 6 p.m. on the 22nd of October 4004 BC. But while humanity changes rapidly, the physical world seems eternal. Mountains, rivers, everything looks much the same as it did ages ago. To many, it has always existed. The idea of a beginning has never sat comfortably with everyone. The great Greek philosopher Aristotle believed that the universe had no beginning at all, that it has existed eternally. For him, eternity was perfection. Something that has always existed must be more perfect than something that merely began. He believed progress could be explained by cycles, by floods, disasters, and rebirths that periodically reset civilization. This eternal universe view conveniently avoided awkward questions about divine creation. On the other hand, those who believed in a beginning used it as an argument for God, but their view raised equally troubling questions. What was before the beginning, and what was God doing before He created the world? As St. Augustine once joked, perhaps he was preparing hell for those who ask such questions. This paradox deeply intrigued Immanuel Kant. He saw in it a logical contradiction, an antinomy of reason. Thesis: if the universe had a beginning, why did it take an infinite time before it began? Antithesis: if the universe has always existed, why did it take an infinite time to reach the present moment? Kant, like most people of his time, believed that time was absolute. It flowed steadily from an infinite past toward an infinite future, independent of anything that happened within the universe. Then, in 1916, Albert Einstein completed the greatest work of his life, the general theory of relativity. It was far more than just a new theory of gravity. It was a theory of space and time themselves. For the first time in history, humanity possessed a theory that could describe not only the motion of planets and stars, but the evolution of the universe as a whole. According to Einstein, space and time are not fixed, eternal backdrops on which events unfold. They are dynamic, shaped and molded by the matter and energy they contain. Space and time exist only within the universe. They have no meaning outside it. But there was a problem. When Einstein applied his equations to the cosmos, the results didn't match the world as scientists understood it. At that time, it was widely believed that the universe was static and eternal. The cosmos, they thought, consisted solely of one galaxy, the Milky Way, floating in a vast, motionless sea of darkness. The night sky appeared calm and unchanging, and there seemed to be no reason to imagine it otherwise. Einstein's equations told a different story. In his framework, gravity, the mutual attraction between masses, would inevitably cause any static universe to collapse. Matter could not remain perfectly still. The pull of gravity would draw it together. This contradicted the notion of an unchanging cosmos. The contradiction troubled Einstein deeply. And yet, his theory had already demonstrated astonishing accuracy. Using it, Einstein calculated the orbit of Mercury, whose motion had long puzzled astronomers. The result matched decades of observations, exactly a minuscule orbital shift of 43 arcseconds per century. When he saw the numbers align, Einstein's heart began to race. He later said he felt something click inside him. I believe this discovery was undoubtedly the most powerful emotional experience of Einstein's scientific life, perhaps of his entire life. Still, the mystery of the universe remained unsolved. The first to offer a solution was a man who combined science and faith in equal measure. Hubble and Lemaitre, a Belgian priest who was also an engineer, mathematician, and physicist. In 1927, Lemaitre solved Einstein's equations in full and made a stunning prediction. The universe is expanding. Einstein's reaction was immediate and harsh. "Your mathematics are correct," he told Lemaitre, "but your physics is ugly." Lemaitre went further. In 1930, he proposed that our expanding universe had emerged from an infinitely small point, a primordial atom. He called that moment the day without yesterday. Thus was born the idea of the Big Bang. Its author was a priest, but Lemaitre himself saw no religious significance in his theory, yet the implications were enormous. If the universe was expanding, it must once have been smaller, so small, in fact, that it had a beginning. And a beginning inevitably suggests creation, and creation, in turn, evokes emotion. In 1951, Pope Pius XII declared that the Big Bang was proof of the biblical story of Genesis. He proclaimed, "Modern science has revealed the evidence of the majestic fiat lux. Let there be light. Therefore, creation occurred. Therefore, there is a creator. Therefore, God exists." But Lemaitre was not pleased by the papal endorsement. He carefully distinguished science from theology. In a formal protest, he insisted, "Such a theory remains entirely outside the scope of religious questions. A theory, however, is one thing, evidence is another." At the dawn of the 20th century, astronomers noticed faint, cloudy patches scattered across the sky. No one knew what they were. Some thought they were mere clouds of gas within our own galaxy. Others suspected something more profound. One of them was Edwin Hubble, a former lawyer turned astronomer who worked with the world's most advanced telescope on Mount Wilson. In 1925, Hubble discovered special kinds of stars within these mysterious nebulae Cepheids, whose brightness changed with precise regularity. A few years earlier, a young woman named Henrietta Leavitt had made an astonishing discovery. Working as a computer at the Harvard Observatory, because women weren't allowed to operate telescopes at the time, she noticed a striking pattern. The brighter the Cepheid star, the longer its cycle of flickering. It was an unshakable law of nature. If you knew the period of a Cepheid's flicker, you could determine its true brightness. and by comparing that with its apparent brightness, you could calculate its distance. Hubble built upon Leavitt's insight. He measured the distance to Cepheid stars in the Andromeda Nebula, and the result stunned the scientific world. These stars were far too distant to belong to our own galaxy. Andromeda, it turned out, was another galaxy altogether, an island universe, almost a mirror image of the Milky Way. In an instant, the scale of the known universe increased millions of times. Hubble showed that many of those faint smudges of light in the night sky were not gas clouds at all, but other galaxies, colossal clusters of stars like our own, separated from us by unimaginable distances. To appear so small and faint, their light must have traveled for millions, perhaps billions of years before reaching our eyes. Clearly, the universe could not have begun a few thousand years ago. Hubble could have stopped there, content with having expanded the universe itself, but he didn't. He continued measuring the distances and motions of ever more distant galaxies and made an even more astonishing discovery. To understand it, we need to return to 1665, when a young Isaac Newton performed experiments with light. He passed a thin beam of sunlight through a prism in a darkened room lit only by a single slit in the shutter. The beam spread into the familiar colors of the rainbow. Newton realized that sunlight contained all colors. He was right. A century and a half later, scientists examined this dispersed light more carefully. They noticed dark bands interrupting the color's absorption lines and discovered that these lines were produced by gases in the sun's atmosphere, which absorbed light at specific wavelengths. To their astonishment, these wavelengths matched those of known elements on Earth: hydrogen, oxygen, iron, sodium, and others. For the first time, we knew that the stars are made of the same elements as our planet. In 1868, astronomers discovered strange spectral lines in the light of the sun lines that did not match any known element on Earth. They named the new element helium. Only a generation later was helium finally found here on our planet. Decades afterward, astronomer Vesto Slipher began studying the spectra of distant nebulae. He noticed something puzzling. All their spectral lines were shifted. It reminded him of the Doppler effect, the same phenomenon that makes a train's whistle sound higher as it approaches and lower as it moves away. The same rule applies to light. If a light source moves away, its wavelength stretches and shifts toward the red end of the spectrum. If it approaches, the light shifts toward blue. Slipher found that almost all galaxies appeared redder. They were moving away from us. Then Edwin Hubble compared his distance measurements of galaxies with Slipher's velocity data. The pattern was unmistakable. Nearly every galaxy was receding, and the farther away a galaxy was, the faster it moved. This relationship became known as Hubble's law. The universe was expanding. Galaxies were not static, they were drifting apart. The discovery of the expanding universe was one of the greatest revolutions of the 20th century. It changed forever how we think about the cosmos and its origin. Imagine yourself living a century ago, hearing that almost every galaxy is moving away from us, and that those twice as distant move twice as fast, while those 3 times as distant move 3 times as fast. The first obvious thought would be, we must be at the center of the universe, but that's not true. To understand Hubble's law, we must step outside the universe in our imagination. Picture a balloon. Draw dots on its surface at random. These are the galaxies. Now, start inflating it. As the balloon expands, all the dots move away from one another. Now, imagine you're an ant sitting on one of those dots. From your point of view, all the other dots are receding. The farther away they are, the faster they seem to move. If you crawl to a different spot on the balloon, the pattern doesn't change. The same rule applies. The expansion doesn't depend on where you are. It's the balloon itself that's stretching. The same thing is happening in our universe. Space itself expands like the surface of an inflating balloon. Galaxies are not flying through space. Rather, space between them is stretching. From every galaxy's perspective, all the others appear to be moving away, as if each one were at the center. But there is no true center. The entire universe is expanding all at once. Hubble not only discovered the link between a galaxy's distance and its speed, but also estimated the rate of expansion. His data suggested that galaxies 3 million light-years away were moving apart at 500 kilometers per second. If galaxies are receding now, they must once have been closer together. Since gravity is an attractive force, it should have slowed their motion. Galaxies now separating at 500 kilometers per second must have moved even faster in the past. Even if we assume a constant speed, we can simply rewind the motion backward in time. Eventually, all galaxies converge at the same point, at the same moment. Hubble's calculations suggested that this happened 1.5 billion years ago. But there was an obvious problem. By 1929, geologists already knew that the Earth itself was more than 3 billion years old. How could the planet be older than the universe? The error turned out to be in the distance scale. Hubble's estimates of Cepheid distances were systematically off. It took decades of refinement to correct them. Modern measurements now put the age of the universe at about 13.8 billion years. At the moment of its birth, everything that exists today, every galaxy, every atom, was compressed into a single point in space. But was there really a Big Bang? Not everyone was satisfied with the idea of a beginning. Many scientists felt that such an event violated the laws of physics. Some preferred to invoke an external cause, a divine creator. Others proposed new theories that tried to preserve an eternal universe. One of the most famous was the steady-state theory. According to it, the universe expands but never truly changes. As galaxies move apart, new matter continuously forms between them, giving rise to new galaxies. The universe, therefore, exists forever and always looks roughly the same. This idea could be tested through observation. A team of radio astronomers at Cambridge, led by Martin Ryle, studied faint sources of radio waves. They found that these sources were distributed uniformly across the sky and lay far beyond our own galaxy. The fainter the source, the farther away it was. But there were more faint sources than the steady-state theory predicted. This meant that the universe had once been denser than it is now, contradicting the steady-state model. For this and other reasons, the theory was eventually abandoned. The Big Bang theory has undergone some of the most rigorous and meticulous testing in the history of science. Physicists calculated that if the universe truly began as a hot, dense fireball, then the light elements, hydrogen, helium, and a trace of lithium should have formed within the first few minutes of its existence. Look at this photograph. In my view, it is one of the most breathtaking images ever captured by the Hubble Space Telescope. It shows a distant spiral galaxy, its light traveling more than 50 million years across space to reach us. That galaxy alone contains about 100 billion stars. At its bright core, around 10 billion stars are packed together. But notice the single, brilliant point in the lower left corner. It shines almost as brightly as the entire galactic center. You might assume it's a nearby star from our own Milky Way that happened to slip into the frame, but no. It belongs to that same distant galaxy, 50 million light-years away. It is a supernova, a star that has exploded, one of the brightest fireworks in the cosmos. When a star explodes, it can shine for a month with the light of 10 billion suns. Fortunately, such explosions are rare about once every 100 years in a galaxy. But we are lucky that they happen at all, because without them, we would not exist. Every atom in your body heavier than lithium was born inside a star. The atoms in your left hand may have come from one star, those in your right hand from another. We are, quite literally, children of the stars, our bodies woven from ancient stardust. How do we know this? Because we can trace the history of the Big Bang all the way back to when the universe was just 1 second old. At that moment, all matter was compressed into a searing plasma at a temperature of 10 billion degrees. Under such conditions, protons and neutrons collided and fused easily, creating the first atomic nuclei. As the universe expanded and cooled, these nuclei combined to form only the lightest elements, hydrogen, helium, and small amounts of deuterium and lithium. Calculations show that nothing heavier than lithium could have formed in that primordial fireball, and these calculations match observation perfectly. The predicted and measured abundances of these elements, spanning differences of 10 billion-fold, agree with astonishing precision. This is one of the greatest triumphs in modern science, and compelling evidence that the hot Big Bang really happened. Lithium might matter to a few, but for most of us, it's the heavier elements, carbon, nitrogen, oxygen, iron, that make life possible. None of these were born in the Big Bang. They were forged in the nuclear furnaces of stars and released only when those stars exploded, scattering their ashes across the galaxy. The last supernova in our own Milky Way was observed by Johannes Kepler in 1604. Over the entire history of our galaxy, roughly 200 million stars have exploded, enriching space with the elements of life. Today, astronomers use these stellar explosions as cosmic beacons. A particular class of supernovae serves as standard candles, objects of known brightness that allow us to measure astronomical distances with extraordinary accuracy. The brighter the supernova, the longer it shines. Though explosions occur only once every 100 years in a typical galaxy, the universe is vast beyond measure. Point a telescope toward any seemingly empty patch of sky, no larger than a dime held at arm's length, and you will see 100,000 galaxies. Every night, in that endless darkness, several stars explode. Through these cosmic beacons, astronomers refined the rate of the universe's expansion. It turned out to be about 7 times smaller than Hubble originally estimated. From Newton to Hubble, from Henrietta Leavitt to the giant observatories orbiting Earth today, 4 centuries of science have built a coherent and awe-inspiring picture of reality. Our universe was born in fire and has been expanding ever since. Every new discovery continues to confirm this grand design. Nothing is collapsing. Nothing is breaking apart. The Big Bang Theory stands on a solid and luminous foundation. Once we established that the universe had a beginning, a new question naturally arose. How will it end? In 1970s, astronomers faced a new cosmic mystery. The stars and galaxies were moving too fast. According to the known laws of physics, these galaxies should have torn themselves apart long ago. Something didn't add up. There had to be more to the universe than what our eyes, or even our telescopes, could see. The quest for an answer began with Vera Rubin. She measured the rotation speed of our own galaxy. By observing the motion of stars and glowing gas at various distances from the galactic center, Rubin noticed something extraordinary. The stars near the edges were moving much faster than gravity should have allowed. If we accounted only for the visible matter, stars, gas, and dust, the galaxy simply shouldn't have been able to hold itself together. There had to be far more mass hidden within it, something invisible, something dark. Physicists initially wondered if this unseen matter might just be hidden objects, rogue planets, faint asteroids, or burned-out stars. But the calculations didn't fit. There was simply too much of it, 10 times more dark matter than ordinary matter. There weren't enough protons and neutrons in the entire universe to explain it. It became clear that most of the cosmos consists of something completely unknown, particles that don't exist here on Earth, something that drifts silently among the stars and governs the motion of galaxies. For young physicists, this was exhilarating. It opened 3 entirely new frontiers. First, they could try to calculate how many of these particles should exist in the universe. Second, they could attempt to detect them by building underground detectors and waiting for a dark matter particle to pass through Earth. But the third was the most profound. The amount of dark matter determines the fate of the universe. Einstein had shown that space itself can curve. Depending on how much matter it contains, the universe can take one of 3 possible shapes. If it's closed, space curves like the surface of a sphere. If it's open, it curves like a saddle. And if it's flat, it stretches endlessly like a sheet of paper. In a closed universe, if you could travel far enough in one direction, you might eventually see the back of your own head. Expansion would one day stop, and the cosmos would collapse again in a big crunch, the reverse of the Big Bang. In an open universe, expansion would never end. Galaxies would drift farther and farther apart until the night sky faded to darkness. And in a flat universe, expansion would slow but never quite stop, a delicate balance between the 2 extremes. To determine which shape our universe has, astronomers needed to weigh all the matter within it, including the dark matter. But how do you weigh something that can't be seen? The answer came through gravity. In 1936, Einstein published a short paper describing how massive objects can bend light, an effect now known as gravitational lensing. Einstein himself dismissed it as a mere theoretical curiosity, saying, "The chances of observing this phenomenon are small." But he was wrong. Astronomer Fritz Zwicky immediately recognized its importance. He realized that galaxies and clusters of galaxies could act as giant cosmic lenses, magnifying the light of more distant objects. And most importantly, the amount of bending could reveal the mass of whatever caused it. Zwicky was a visionary. As early as 1933, he had noticed that galaxies in large clusters were moving far too fast to be held together by their visible mass alone. He concluded that these clusters must contain enormous amounts of unseen matter, hundreds of times greater than what could be observed. Zwicky, though largely ignored at the time, was in fact the first person to discover dark matter. Decades passed. In 1987, astronomers finally witnessed gravitational lensing in action, a distant quasar whose light was magnified and split by a galaxy along the way. Then, in 1998, the Hubble Space Telescope captured this. The image shows a galaxy cluster 5 billion light-years away. Behind it, another 5 billion light-years farther, lies yet another galaxy. Its image is warped into long, glowing arcs, repeating several times. It's a mind-bending picture. Every dot you see is not a star, but a galaxy each containing around 100 billion stars, hundreds of billions of planets, and perhaps civilizations long vanished. We are seeing this cluster as it was 5 billion years ago. The light began its journey long before the sun and Earth even formed. Many of the stars in this photograph no longer exist. They exhausted their nuclear fuel eons ago. Those distorted arcs reveal where the invisible mass lies. Physicists traced the light's path backward, reconstructing the hidden distribution of matter inside the cluster. The result was astonishing. Most of the mass wasn't inside the galaxies at all, but between them. Dark matter turned out to be 40 times more abundant than visible matter, and if you count only the stars, the ratio rises to 300 to 1. Dark matter is everywhere, in galaxies, between them, and even in the vast spaces between clusters. More importantly, it shapes the structure of the entire universe. Physicists hoped there might be just enough dark matter to make the universe flat, because a flat universe is the only one that is mathematically elegant. That would require 100 times more dark matter than ordinary matter. But observations told a different story. All matter, both visible and dark, accounted for only about 30% of the density needed for flatness. Visible matter alone makes up less than 1% of the total. These discoveries launched an entirely new branch of experimental physics. Dark matter particles are streaming through us right now, millions of them passing through our bodies every second. We don't feel them because they almost never interact with ordinary atoms. Almost. That single word, almost, gave physicists hope. If the interaction is not strictly zero, we might someday detect them. To that end, vast detectors were built deep underground, shielded from cosmic rays, waiting patiently for the rarest of events, the collision of a dark matter particle with an atomic nucleus. At the same time, scientists at the Large Hadron Collider tried to create dark matter particles artificially. A great race began to be the first to catch the invisible. Though no one has yet identified what dark matter truly is, these efforts revealed how much of it there must be. Einstein would have been astonished to learn that his little note about gravitational lensing turned out to be one of the most useful insights in cosmic history. Amplified by new instruments and ideas, it led to the discovery of dark matter and to a giant leap in human understanding. By the early 1990s, the so-called Holy Grail of cosmology seemed within reach. Observations suggested that we lived in an open universe that would expand forever. Or so it seemed. Look around your room. See that wall? You can't see what's behind it because it's opaque. It blocks light. The universe has a similar horizon. When we look into deep space, we are looking into the past. The light from distant galaxies has traveled for millions or even billions of years before reaching us. The farther we look, the farther back in time we see. But there is a limit. When the universe was only 300,000 years old, it was so hot that atoms couldn't yet exist, only plasma, a seething soup of protons and electrons. That plasma was opaque, like a wall. Then, as the universe cooled, protons and electrons combined to form hydrogen atoms. The cosmos became transparent. Light could finally travel freely. That ancient light is still traveling today. 13.8 billion years later, we know it as the cosmic microwave background radiation, the afterglow of the Big Bang itself. In 1965, 2 engineers in New Jersey accidentally discovered it. They weren't looking for the origin of the universe. They were simply trying to remove a strange background noise from their antenna. The noise turned out to be the faint whisper of creation. For their discovery, they won the Nobel Prize. It's almost comical that this signal was literally everywhere, right under humanity's nose. Remember old televisions? When a channel ended and the screen turned to static, that flickering noise of black and white dots, about 1% of it was light from the Big Bang. The cosmic microwave background carries the imprint of the infant universe. Within it are the seeds of all future galaxies, stars, and planets, tiny ripples of matter that would grow over billions of years into everything we see today. But perhaps most importantly, this light contains a secret message. It can tell us about the shape of the universe. Back in the 19th century, the great mathematician Carl Friedrich Gauss realized that to know the shape of space, one must measure the angles of a triangle. On a flat surface, the angles always add up to 180 degrees. On a curved surface, they add up to either more or less. Gauss even attempted to measure the curvature of our space itself. Using maps of mountains across Germany, he calculated the angles of enormous terrestrial triangles. But his instruments were too crude to detect any deviation. The Russian mathematician Nikolai Lobachevsky proposed a more ambitious idea: use the stars. He wanted to measure the triangle formed by the Earth, the Sun, and Sirius, the brightest star in the night sky. But even that celestial triangle proved far too small to reveal any curvature. It would take a century and a half before humanity finally had a way to measure the shape of the universe directly. The key lay hidden in the cosmic microwave background radiation, the afterglow of the Big Bang. When the universe was about 300,000 years old, the largest clumps of matter that had begun to collapse under gravity were roughly 300,000 light-years across. Why that number? Because gravity, like light, travels at a finite speed. In 300,000 years, no signal could travel farther than 300,000 light-years. These ancient clumps left subtle imprints on the microwave background regions, slightly hotter or colder than average. The true size of those hot and cold spots is determined by physics, but their apparent size in the sky depends on the geometry of the universe. In a flat universe, light travels in straight lines, and those spots appear exactly as large as they should. In a curved universe, light bends, making the same physical objects appear larger or smaller. In 1997, a team of scientists launched a high-altitude balloon over Antarctica, carrying a sensitive microwave detector. The project was called Boomerang because the balloon would circle the frozen continent and return to its launch site. For 2 weeks, it floated high above the cold, dry air, mapping the microwave sky with unprecedented precision. The results were astonishing. The largest hot and cold spots in the cosmic microwave background had an angular size of 1 degree, exactly what theory predicted for a flat universe. The mathematically elegant cosmos that theorists had dreamed of turned out to be real. Later, NASA's WMAP satellite produced an even sharper map of the entire sky. Its data confirmed the result to within 1%. We live in a flat universe. But the discovery created a new problem. All previous measurements showed that the combined mass of visible matter and dark matter accounted for only 1/3 of what was needed to make the universe flat. Something else had to be filling the remaining 70%. Where was this missing energy hiding? The answer was right in front of us, woven into space itself. Cosmologists found themselves trapped in a paradox. Observations proved that the universe was flat, but when they weighed all known matter, including dark matter, it fell short. The missing 70% of the universe's energy was invisible, omnipresent, and utterly mysterious. The solution lay in Einstein's most audacious idea. In 1917, while formulating general relativity, Einstein faced a dilemma. His equations implied that the universe could not be static. It must either expand or contract. But at the time, everyone, including Einstein, believed that the cosmos was eternal and unchanging. To make the equations fit that worldview, he added an extra term, a cosmological constant, which introduced a gentle, repulsive force to counteract gravity. This allowed for a perfectly balanced, static universe. But when Hubble later discovered that the universe was expanding, Einstein quickly discarded the constant, calling it his greatest mistake. Yet, eliminating the cosmological constant turned out to be impossible. Its meaning was profound. Even empty space is not truly empty. It possesses energy. The idea sounds absurd. A child could say that a vacuum contains nothing. So how can nothing have energy? But that's before one learns about quantum mechanics. In 1929, the brilliant physicist Paul Dirac attempted to unite quantum mechanics with relativity. He derived an equation describing how electrons behave at high speeds. The math worked beautifully, except for one puzzling prediction. His equation required the existence of an entirely new kind of particle, identical to the electron, but with the opposite charge. Dirac was baffled. Only electrons and protons were known at the time. He tried to argue that his mysterious new particle must somehow be the proton, but his colleagues quickly showed that this was impossible. Then, just 2 years later, the particle was discovered in cosmic rays. It was exactly what Dirac's theory had predicted, an antiparticle of the electron. They named it the positron. Dirac later admitted, "This equation was smarter than I was." It was Richard Feynman who first understood what was truly happening in empty space. Feynman realized that Einstein's theory of relativity tells us that observers moving at different speeds will measure quantities like distance and time differently. As an object approaches the speed of light, time slows down for it. If it could somehow exceed that ultimate speed, it would appear to move backward in time. That's one reason the speed of light is regarded as the cosmic speed limit. The key idea of quantum mechanics is Heisenberg's uncertainty principle. For some pairs of quantities like position and momentum, it is impossible to know both values precisely at the same time. The shorter the time over which you measure something, the less precisely you can know its energy. This leads to a startling conclusion. For extremely short intervals so brief that we can't precisely measure velocity, quantum mechanics allows particles to behave as if they were moving faster than light. And if they do, relativity says they must behave as if they're moving backward in time. Feynman decided to take this bizarre idea seriously. He imagined an electron traveling through space, sometimes appearing to move faster than light. Then he realized another observer, viewing the same process, would describe it differently. The electron would move forward in time, then backward, then forward again. But here's the twist. A negative charge moving backward in time is mathematically equivalent to a positive charge moving forward in time. As Feynman later explained, this interpretation of the equations implied that every electron must have a mirror twin identical in mass and behavior, but with the opposite electric charge. In other words, the positron. Feynman's drawing can be interpreted as follows. One electron moves, then, at another point in space, a positron-electron pair is created out of nothing. Then the positron meets the first electron, and the two annihilate. Eventually, a single moving electron remains. If that doesn't confuse you, consider this. For a while, even if you start with only one particle and end with only one particle, for a short time you have three moving particles. In the brief moment in between, at least for a while, something is born out of nothing. A paradox. You start with one particle and end with one particle, but in between, there are three. Something was born out of nothing. These fleeting intermediate particles exist for such short times that they cannot be measured directly. They are called virtual particles. According to quantum mechanics and relativity, such particles are not just possible, they are inevitable. For an instant, they can even borrow energy from nowhere, as long as they return it quickly enough. Virtual particles may sound absurd, pure fantasy, but their effects can be measured with astonishing precision. In 1947, physicist Willis Lamb measured the energy levels of hydrogen with unprecedented accuracy down to 1 part in 100 million. The result differed slightly from the predictions of Dirac's elegant theory. The world's leading theorists set to work. The answer was found when they accounted for the influence of virtual particles. A hydrogen atom is not just a proton and an electron around them. Countless electron-positron pairs are constantly appearing and disappearing. The virtual electrons are drawn toward the proton, while the positrons are repelled, slightly distorting the charge distribution inside the atom. When this effect was added to the calculations, theory and experiment matched perfectly to within 1 part in a billion. It became the most accurate prediction in the history of science. But that triumph revealed something terrifying. If virtual particles are constantly flickering into and out of existence, then even empty space must contain an enormous amount of energy. Physicists tried to calculate it, and the result was catastrophic. The predicted energy of empty space was 10 to the power of 120 times greater than the energy of all known matter in the universe. A 1 followed by 120 zeros. If the vacuum really possessed that much energy, its repulsive force would have blown apart not just the Earth, but the entire cosmos in the first fractions of a second after the Big Bang. No stars, no planets, no people. This became known as the vacuum catastrophe, the single worst prediction in the history of physics. For decades, scientists knew something was deeply wrong, yet they slept soundly. Their reasoning was simple. Surely the energy of empty space must be zero. Zero felt natural. Zero was elegant. In physics, opposing quantities often cancel each other perfectly. But to produce a tiny non-zero value by subtracting two vast numbers each correct to 120 decimal places was beyond anything science had ever encountered. So theorists remained confident that the final, unified theory would make the vacuum's energy vanish exactly to zero. But nature had a surprise. It turned out that the energy of empty space is not zero. In fact, it accounts for the missing 70% of the energy required for a flat universe. It had been hiding in plain sight in space itself. Einstein's cosmological constant, once dismissed as his greatest mistake, was vindicated. Empty space does have energy, and that energy creates a repulsive force. Not as overwhelming as the monstrous value predicted by quantum theory, but precisely the amount needed to make the universe flat. Einstein's greatest blunder became one of the greatest discoveries in cosmology. The vacuum is not empty after all. It is alive with invisible activity, and it determines the fate of the entire cosmos. In 1995, physicists Lawrence Krauss and Michael Turner proposed a radical idea. All the evidence suggested that the universe lacked enough matter to make its geometry flat. They hypothesized that the missing 70% of energy was hidden in empty space itself. If the vacuum contained energy, it would create a repulsive force, a kind of cosmic antigravity. In that case, the expansion of the universe should be accelerating, not slowing down. And if that were true, distant supernovae would appear dimmer than expected, because their light would have traveled farther and taken longer to reach us. 3 years later, in 1998, 2 independent teams of astronomers tested the idea. The results were sensational. The expansion of the universe was indeed accelerating. The distance velocity graph for distant supernovae curved upward, not downward. There was only one possible explanation. Anti-gravity was real. Even more astonishingly, the amount of this mysterious force matched the prediction exactly: 30% matter and 70% dark energy. Science magazine called it the scientific breakthrough of the year. A stunned Albert Einstein appeared on the cover, as if the universe itself had resurrected his abandoned cosmological constant. The following decade brought an avalanche of confirmations. The WMAP satellite precisely measured the age of the universe, 13.8 billion years, an age impossible to explain without dark energy. Other surveys traced how galaxies clustered across cosmic history. The data matched perfectly with the same ratio: 70% dark energy. Astrophysicist Adam Rees made another key discovery. By tracing the expansion deep into the past, he identified a transition point. In the early universe, matter dominated, and expansion was slowing. But about 5 billion years ago, dark energy took over, and the universe began to accelerate. Today, the picture of reality borders on the absurd. 95% of the universe is invisible. Ordinary matter, everything we can see, makes up only 5%. The rest is dark matter and dark energy. We live in a vast sea of the unknown. Dark energy behaves like Einstein's cosmological constant. Its density doesn't change with time, yet its origin and nature remain the greatest mystery in modern physics. We don't know where it came from, or why it has exactly the value it does. Why did it become dominant only recently in cosmic history? Is it a coincidence or a pattern woven into the universe itself? The future of the entire cosmos depends on the answers to these questions. The universe had given cosmologists 2 astonishing revelations. The bad news: empty space really does contain energy. The good news: there's just enough of it to keep the universe from tearing itself apart in its first moments. But that raised yet another mystery. The universe turned out to be almost perfectly flat. How could that be? Imagine trying to balance a pencil perfectly upright on its tip. The tiniest imbalance and it falls. The geometry of the universe is exactly the same. If the early universe had been even slightly curved, that deviation would have grown exponentially over time. Over its lifetime, the universe has expanded by nearly 1 trillion-fold. If, in the first second, its density had been only 10% less than that of a perfectly flat universe, today it would differ by a factor of 1 trillion. And yet, we observe near-perfect flatness. Everything seems fine-tuned with astonishing precision. Equally mysterious is the cosmic microwave background. Its temperature is almost perfectly uniform across the entire sky to within hundredths of a percent. The universe is astonishingly smooth on the largest scales, far more uniform than a freshly painted wall. But how did the universe become so smooth? In the standard Big Bang model, distant regions of the cosmos were never in contact with each other. They never exchanged light or heat. So how did they agree to have exactly the same temperature? In 1981, a young physicist at Stanford named Alan Guth proposed a brilliant answer. He called it inflation. Guth realized that in the earliest fraction of a second, the universe could have undergone a phase transition like when water suddenly freezes into ice. Or imagine a supercooled bottle of beer. You open it, lower the pressure, and the liquid instantly crystallizes, releasing a burst of latent energy. In the same way, the newborn universe may have become stuck in an unstable state, a false vacuum, and then suddenly transitioned to a more stable one, releasing an enormous amount of energy. That energy acted like a cosmological constant, triggering an explosive expansion of space faster than the speed of light. In a split second, the universe grew by a factor of 10 to the power of 28. Our entire observable cosmos once fit inside a region smaller than a proton, small enough for everything within it to reach thermal equilibrium. Then, inflation stretched that microscopic patch to cosmic size. That's why the cosmic microwave background radiation is so uniform, it still carries the memory of that ancient thermal bath. Inflation also solved the flatness problem. When you inflate a balloon, its surface becomes smoother and flatter. The same thing happened to the universe. Any tiny initial curvature was stretched to near perfection. But inflation predicted something even more extraordinary. On microscopic scales, empty space is never truly empty. It seethes with quantum fluctuations. Virtual particles are constantly appearing and vanishing. Normally, these fluctuations average out, leaving no trace. But inflation froze them in place, stretching them across vast regions of space and turning them into slight differences in density. Those minute ripples became the seeds of all cosmic structure, galaxies, stars, planets, and, ultimately, us. If inflation is real, then everything we see, every atom, every person, every world, exists because of quantum fluctuations in the void. We literally emerged from nothingness. But where did the energy for inflation come from? How did a tiny patch of space inflate into an entire universe? Alan Guth called it the ultimate free lunch. The secret lies in gravity. Unlike other forces, gravity allows energy to be negative. Think back to high school physics. When you throw a ball upward, it has positive kinetic energy from motion and negative potential energy from gravity. If you throw it hard enough, about 11 kilometers per second, it escapes Earth's pull. At that speed, its positive and negative energies exactly cancel. The total energy is zero. The universe works the same way. In a flat universe, the positive energy of matter and radiation is perfectly balanced by the negative energy of gravity. The energy of empty space creates negative pressure. As the universe expands, it performs work on the vacuum, maintaining a constant energy density. It's as if the cosmos is expanding for free. From a tiny region with almost zero energy, a vast universe emerged, yet its total energy remains zero. The positive energy of matter and light is exactly balanced by the negative energy of gravity, a perfect equilibrium. When cosmologists finally measured the curvature of the universe and found it to be zero, many breathed a sigh of relief. The universe really could have arisen from nothing, and this nothing had zero energy. We live in an extraordinary moment in cosmic history. The universe around us overflows with galaxies, stars, and countless worlds. The faint afterglow of the Big Bang still whispers across the darkness, carrying the memory of the universe's childhood. The Hubble expansion reveals that space itself is alive, stretching, changing, and evolving. Yet beneath all this beauty lies a shadow. An invisible force, dark energy, is driving space to expand faster and faster. Soon, distant galaxies will begin to recede from us faster than light. Their glow will no longer be able to keep pace with the expansion of space. One by one, they will fade beyond the cosmic horizon. First, their light will shift into red, then infrared, then to the long wavelengths of radio. Eventually, the waves will stretch so far that they'll exceed the size of the visible universe, and those galaxies will vanish completely from view. In 2 trillion years, every one of the 400 billion galaxies we can see today will have disappeared beyond reach. Only the galaxies of our local group, the Milky Way, Andromeda, and their small companions will remain. Even they will one day merge into a single giant galaxy. Imagine the astronomers of that far future. Some stars will still burn. There may still be planets with oceans, perhaps even with life. Civilizations might still gaze at the night sky. But when their scientists point their telescopes outward, they will see only one lonely island of light in an otherwise eternal void. Not only will the rest of the universe be gone, but the evidence that it ever existed will vanish too. The expansion will be impossible to measure. There will be nothing left to measure it with. The cosmic microwave background will fade until its temperature is so low it can no longer pass through the plasma of their galaxy. Even the chemical clues will disappear. Today, the abundance of hydrogen and helium matches the predictions of the Big Bang perfectly. But in that distant future, generations of stars will have burned so much hydrogen into helium that the balance will shift. Astronomers then will see a universe whose elements can be explained entirely by stellar evolution. They will have no need for a Big Bang. Those future scientists will do what we do now. They will build models, test them, and follow the evidence. But the evidence will deceive them. They will conclude that they live in a single, eternal galaxy surrounded by infinite darkness. Perhaps one brilliant mind will rediscover Einstein's equations and show that such a system could exist in static space. And everyone will agree because it will fit their observations perfectly. We live in a unique cosmic era, a fleeting window when the universe still reveals its true nature. Only now, for a brief cosmic moment, can dark energy be detected through the acceleration of expansion. In the past, matter and radiation ruled. Dark energy was too weak to notice. In the far future, it will dominate completely, but its presence will be undetectable. As cosmologist Boris Shazer once said, we live in a very special time. The only time when we can experimentally prove that we live in a very special time. This thought should humble us. Even armed with the best instruments and purest reasoning, we can still arrive at a completely mistaken understanding of reality. Perhaps we too are missing something. Perhaps 10 billion years ago, or 100 billion years from now, the universe could be seen in ways forever hidden from us. Yet unlike those who deny evidence or cling to myths, the scientists of that distant future will follow the data faithfully. The tragedy is that the data itself will lie. And so, cosmology will come full circle. The astronomers of the far future will believe, as we once did, that they live in a single, eternal galaxy, surrounded by infinite, silent darkness. As Christopher Hitchens once said, those who marvel that there is something rather than nothing, just wait. Nothing is coming for us. Dark energy, which once pulled everything out of quantum nothingness, will one day return the universe to emptiness. We are just a brief flicker between two eternities of nothing. Yet we humans are addicted to meaning. We see patterns in the noise. We dream that a friend will break his arm. He merely sprains his ankle, and suddenly, we're prophets. Richard Feynman loved to walk up to people and say, "You won't believe what happened to me today." When they asked what, he'd grin and answer, "Absolutely nothing." He was making a point. We forget the thousands of meaningless dreams and notice only those rare coincidences that seem special. The same illusion shapes how we see the universe. Before the discovery of dark energy, physicists believed that every constant of nature must carry deep significance. Why is gravity so much weaker than the other forces? Why is the proton about 2,000 times heavier than the electron? We thought that once we found the ultimate theory, everything would make sense. Then dark energy arrived and shattered that faith. Its value turned out to be 120 orders of magnitude smaller than theory predicted, the worst mismatch between theory and experiment in all of science. It's as if nature picked a number with absurd, almost mocking precision. Worse, we happen to live in a special era when the density of dark energy is roughly equal to that of matter. Only now can it be measured. This violates the Copernican principle, the idea that our place in the cosmos should never be unique. Physicist Steven Weinberg offered a provocative answer. Perhaps there are countless universes, each with a different amount of dark energy. We find ourselves in one with just the right value, simply because we couldn't exist in any other. If dark energy were 50 times stronger, it would have dominated. Two early galaxies would never have formed. Without galaxies, no stars. Without stars, no planets. Without planets, no observers. We live in a universe that allows us to live. Hardly surprising, but only if other universes exist. That idea became known as the anthropic principle, and it led naturally to a bigger, stranger vision, the multiverse. Inflation theory provides the mechanism. Alan Guth showed that a tiny region trapped in a false vacuum could expand exponentially, growing into an entire cosmos. Later, André Linde extended this concept into what he called chaotic inflation. Quantum fluctuations can either stop inflation locally or make it accelerate even more. The result is a landscape that never stops boiling, like an infinite pot of oatmeal where bubbles constantly form and burst. Each bubble becomes its own universe, while the space between them continues to expand. Inflation, in this picture, never ends. New bubble universes are born endlessly, separated by oceans of ever-stretching space. String theory added yet another layer of possibility. According to it, the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings. Different vibrations create different particles like musical notes played on a cosmic violin. But the theory demands 10 dimensions of space and time. 6 of them must be curled up into spaces so small that we can never see them directly. And the way those dimensions fold determines the laws of physics that emerge. Instead of a theory of everything, we seem to have found a theory of anything, a framework that could describe 10 to the power of 500 different universes. Critics joke that string theorists have invented a new kind of darts. First, they throw the dart, then they draw the target around it. And yet, perhaps this is truly how nature works. Maybe the constants of physics are not universal truths, but environmental coincidences, like the climates on different planets. Some physicists have pushed the idea further. If one quantity can be random, why not all? Maybe the great riddles of particle physics, why forces have their particular strengths, why masses take their peculiar values, have no deeper reason at all. If it were otherwise, the universe simply wouldn't allow us to exist. It sounds like the end of science as we know it. Instead of explaining why it must be so, we explain why it can't be otherwise. But for now, these ideas remain hypotheses. The multiverse cannot be observed directly. We can only search for indirect evidence. If a unified theory predicts inflation, predicts the multiverse, and its other predictions hold true, then we may have reason to trust it. The Large Hadron Collider may one day open windows into this new physics, but so far, it has only confirmed what we already knew. Perhaps we are approaching the limits of knowledge itself. Perhaps the constants of nature really are random. Our universe may be nothing more than a single tear in an infinite ocean of possibilities. We may never fully understand why it is the way it is, or perhaps we will. Either way, we must explore every path, not shift responsibility to some incomprehensible creator. To open our minds means to align imagination with evidence, not the other way around, even when the truth makes us uncomfortable. The history of science is the story of illusions collapsing one by one, illusions about our own importance. We are not the center of the solar system, nor the galaxy, nor even the universe. Perhaps we are not the only form of intelligence, nor the only universe at all. So let us return to the oldest question. Why is there something rather than nothing? In science, we must handle the word why with care. We rarely mean purpose. We mean process. When we ask why the Earth is 93 million miles from the Sun, we're not searching for divine intention. We're asking how physical forces shaped that orbit. The better question then is, how is it that there is something rather than nothing? To answer, we must first understand what nothing truly means. Philosophers define it as non-existence, but that doesn't help much. In physics, nothing is not an absence, it has structure. It can have energy. We've already learned that empty space isn't empty. Even without matter or radiation, it contains vacuum energy. Alan Guth showed how that energy could give rise to a universe, a cosmic free lunch. If empty space holds energy, it will expand exponentially. A tiny patch can inflate to the size of an entire cosmos in a fraction of a second. But where does the energy come from? The secret lies in negative pressure. Vacuum energy exerts a push rather than a pull. As the universe expands, matter thins out and cools, but the energy of the vacuum stays constant. Expansion itself fuels the process, creating more space and therefore more energy. It sounds like magic, but it's not. It follows directly from Einstein's general relativity. Negative pressure does the work. Our observable universe could have begun as a microscopically small region of space, effectively empty and yet grown to enormous scales, eventually containing vast amounts of matter and radiation. Without expending a drop of energy, and with enough matter and radiation to explain everything we see today, something can arise in empty space, precisely because the energetics of empty space, in the presence of gravity, are completely different from what we might expect based on common sense. Of course, it seems reasonable to assume a priori that matter cannot spontaneously arise from empty space, so that something, in this sense, cannot arise from nothing. But when we take into account the dynamics of gravitational and quantum mechanics, we see that this practical view is no longer true. This is the beauty of science, and there should be nothing threatening about it. Science simply forces us to reconsider what makes sense for the structure of the universe, not the other way around. Our universe is astonishingly close to perfect flatness, and that's no coincidence. In a flat universe, the total gravitational energy of everything adds up to zero. The positive energy of motion is exactly balanced by the negative energy of gravitational attraction. That's precisely what we'd expect if the cosmos emerged from almost nothing through inflation. Inflation explains not only why the universe is flat, but also why it has the structure we see today. Tiny quantum fluctuations in the early vacuum were frozen in place during that rapid expansion. Those minuscule ripples in density became the seeds of galaxies, stars, and planets. We quite literally evolved out of quantum fluctuations in nothingness. When inflation ended, the energy of empty space transformed into the energy of real particles and radiation. That's when the ordinary expansion of the Big Bang began. Inflation erased all memory of what came before, leaving behind a nearly uniform universe, one that looks the same in every direction, no matter what its initial conditions were. The observation that the universe is flat and that local Newtonian gravitational energy is virtually zero now strongly suggests that our universe arose through a process similar to inflation, a process in which the energy of empty space, nothing, is converted into the energy of something, while the universe became increasingly flatter on all observable scales. When physicists speak of nothing, they don't mean absolute emptiness. They mean a region of space with no matter, no radiation, only energy, and the laws of physics themselves. Admittedly, that already sounds like something. Empty space with energy isn't really nothing at all. To get even that far, we have to assume the existence of space itself and of the laws that govern it. So, we're still far from solving the ultimate problem of how a universe could arise from true nothingness. Be that as it may, this is only the first step. As our understanding expands, we will see that inflation may represent just the tip of a cosmic iceberg of nothingness. Empty space behaves like a restless politician when no one's watching. Who knows what it's up to? Beneath the calm surface, it seethes with virtual particles flickering in and out of existence faster than we can detect. Quantum mechanics runs on a strange principle. If no one is observing, anything is possible. Every system explores all possible states at once, even those that would be forbidden by direct measurement. These virtual particles are like cosmic stockbrokers. They can borrow energy from the vacuum, as long as they pay it back quickly before the inspectors, our measuring instruments, catch them. But sometimes, nature finds loopholes in its own rules. Imagine bringing two charged plates very close together. If the electric field between them becomes strong enough, real particles can escape the vacuum's cotangent-free. Negative charges rush toward the positive plate, and positive charges toward the negative. If the energy gained by the field's collapse exceeds the mass energy needed to create those particles, voila, something is born from nothing. But such a miracle requires monstrous fields. In 1974, Stephen Hawking revealed one of the most astonishing tricks in all of physics. Black holes, the very objects from which nothing can escape, actually emit particles. Imagine this: a particle-antiparticle pair spontaneously appears at the event horizon. One falls in, the other escapes. The one that falls carries negative energy relative to the outside universe. The result is paradoxical, but real. The black hole loses more energy than it gains in mass. It becomes lighter. Over immense spans of time, it evaporates, slowly radiating matter away into space. Every morning, when we wake, we rarely think about a far greater miracle. We exist as matter, not antimatter. Yet, by all logic, the early universe should have contained equal amounts of both. Matter and antimatter should have annihilated one another completely, leaving behind nothing but cold radiation, no stars, no planets, no lovers beneath the night sky, only darkness and cooling photons. In 1970s, scientists began to understand how this cosmic miracle occurred. During the searing first moments after the Big Bang, quantum processes may have produced an infinitesimal imbalance, just one extra particle of matter for every billion pairs. That slight excess was enough. Almost all matter and antimatter annihilated, and from the leftover fraction came every galaxy, every star, every atom in your body. The cosmic microwave background still glows with the faint echo of that annihilation. Nobel laureate Frank Wilczek once compared it to standing on a mountaintop. You stumble, and the direction you fall is random. Gravity itself doesn't choose, but the way you fall is decided by chance. So it is with our universe. The laws of physics demanded that an asymmetry arise, but whether it favored matter or antimatter, that was left to chance. We simply got lucky. Then, in 1980, Wilczek proposed a breathtaking idea. one that reframed the oldest question of all. Why is there something rather than nothing? His answer: because nothing is unstable. The universe may have begun in the most symmetrical state imaginable, absolute emptiness. But perfect symmetry is delicate. That nothing turned out to be unstable. A lower energy state existed, one with slightly broken symmetry. The transition was inevitable. The energy released in that fall became particles, radiation, and space itself. That moment was the Big Bang. No creator required, no divine spark. Nothing gave birth to everything, because the laws of nature left it no choice. The symmetric void fractured into an asymmetric universe filled with matter. Empty space boils with virtual particles. Under extreme conditions, the virtual becomes real. Black holes radiate from nothing. Quantum processes shatter the perfect balance again and again. Everywhere we look, nothing tries to become something. Under the right conditions, creation isn't miraculous, it's inevitable. The universe doesn't need permission to exist. It simply can't help it. Einstein once asked a profound question: did God have a choice in creating the universe? By God, he didn't mean the biblical deity, but the very order of nature itself. In other words, are the laws of physics unique? Is our universe the only possible one? Or could there have been others? So far, we've explored how something can emerge from empty space. But space itself is already something. It has structure, energy, and laws. So let's push further. What if we merge quantum mechanics with general relativity? Then, the strange rules of quantum uncertainty would apply not only to particles within space, but to space-time itself. Richard Feynman developed a revolutionary method known as the path integral. In the quantum world, a particle doesn't travel along a single route. It explores every possible path at once, including those that would be forbidden in classical physics. Stephen Hawking was the first to apply this principle to space-time itself. If quantum mechanics governs not just particles within space, but the very fabric of space and time, then space-time can explore all possible geometries. On microscopic scales, it becomes a kind of seething froth, curved, twisted, punctured with tunnels and handles. Remember the virtual particles that constantly flicker in and out of existence? By the same logic, tiny virtual universes can appear and vanish. Each one represents a complete, self-contained space-time. But there's an important distinction. While ordinary virtual particles must vanish quickly, a universe whose total energy is zero faces no such limitation. Photons with exactly zero energy can persist indefinitely, unbound by the uncertainty principle. The same could be true for entire universes. A flat universe, like ours, can have zero total energy on average. But the most natural case is a closed universe, one in which space curves back on itself. In a closed universe, if you were to travel far enough in one direction, you would eventually return to your starting point, seeing, as Hawking liked to say, the back of your own head. The total energy of such a cosmos is perfectly balanced. The positive energy of matter and radiation is exactly offset by the negative energy of gravity. It's similar to electric field lines emerging from a positive charge, wrapping around the universe and converging on a negative one, canceling each other completely. But there's a catch. A closed universe is unstable. It expands to a maximum size, then collapses again within a fraction of a second. Yet nature offers a loophole. If inflation begins before that collapse, a tiny closed universe can balloon to a vast size and become nearly flat. After roughly 100 doublings in scale, the curvature becomes indistinguishable from flatness. Such a universe can persist for billions of years, like ours. Here's what we've learned. In the framework of quantum gravity, universes can, and inevitably will, spontaneously appear out of nothing. By nothing, we now mean the absence of space, time, and anything else whatsoever. These universes can contain matter and radiation as long as their total energy is zero. Inflation is what allows them to survive. The only long-lived universes are those that are nearly flat, precisely what we observe. The message from nature is clear. Quantum gravity doesn't merely allow universes to arise from nothing, it demands it. Nothingness, in the most radical sense, the total absence of space and time, is inherently unstable. And the properties of the universes born from this instability match the one we inhabit. Does this prove that our universe came into being this way? Of course not, but it makes the scenario profoundly plausible. We have stripped away yet another objection to creation from nothing. Once, we thought space itself was necessary for creation. Then we discovered that even space could emerge spontaneously. Now, one final mystery remains. Perhaps even the laws of physics themselves are not fundamental. The main problem with the idea of creation has always been that it implies an external cause, something beyond the system that sets the rules. Traditionally, that's where people invoke God, an external agent existing apart from space, time, and the physical world. But God, as an explanation, merely shifts the question rather than answers it. It's like what the cognitive scientist Steven Pinker once pointed out in Moral Philosophy. Many believers argue that without God, there can be no standard of good and evil, that God defines what is right and wrong. But imagine if God decreed that murder were moral. Would it then be good? Most believers would instinctively say no, because they already recognize a deeper standard beyond divine command. If even God appeals to reason or conscience, then the intermediary becomes unnecessary. It's the same with the creation of the universe. In every model we've discussed so far, some underlying rules were already in place, the laws of physics. But that raises an even deeper question. Where did those rules come from? There are only two possibilities. Either they were imposed by divine will, or they arose naturally. The first leads to a paradox. If God made the laws, who made his? The traditional answer is that God is the cause of all causes, the first cause. Aristotle recognized the same problem. Every cause must itself have a cause. To avoid an infinite regress, he concluded that motion, and therefore the universe, must be eternal. God, the unmoved mover, was eternal as well. In Aristotle's view, the chain of why questions ends there, but only at the cost of introducing an omnipotent being for whom there is no independent evidence. The modern picture of the cosmos offers a very different kind of solution, the multiverse. Our universe might be just one among an infinite number of others, each governed by different physical laws. That possibility carries an unsettling implication. Physics may be environmental rather than fundamental. The laws of nature could be as contingent as the distance between Earth and the Sunday. We live here not because this distance is special, but because life would be impossible anywhere else. Anthropic reasoning, however, is slippery. It resists clear predictions. We have no idea what the probability distribution of constants might be across an infinite landscape of universes. Yet the multiverse changes the rules of the game. The demand for a unique, necessary set of physical laws fades. If the laws themselves are random, there is no ultimate cause to seek. The principle becomes simple. Everything not forbidden is permitted. In such a scenario, universes like ours are inevitable, not exceptional. No mechanism demands our specific laws. They simply happen to work. Perhaps there is no final theory at all. For many scientists, this idea is deeply unsettling. They entered physics hoping to discover why the universe must be exactly as it is. If all laws are accidental, then the very purpose of science seems to dissolve. But there is solace in the words of Richard Feynman, who said, "People often ask me, are you looking for the ultimate laws of physics? No, I just want to learn more about the world. If it turns out there's a simple law that explains everything, great. If the world is like an onion with millions of layers, fine too. I like to learn." A multiverse could contain infinite realms of nothing and regions of something. In that case, the question, why is there something rather than nothing, becomes almost trivial. There is something because, if there weren't, we wouldn't be here to ask. It's an anticlimactic answer, but history has shown that the profound and the trivial are not always what they seem. The universe is far stranger than anything our imagination could invent. Modern cosmology forces us to confront ideas that would have been unthinkable a century ago, and one final twist remains. Hidden inside the question, why is there something rather than nothing, is an unspoken assumption that something will always exist. But that assumption, too, may be false. Implicit in the question of why there is something rather than nothing was the solipsistic expectation that something would continue to exist, that the universe had somehow progressed to accommodate our presence, as if we were the pinnacle of creation. Far more likely, based on everything we know, is the possibility that in the future, nothingness will reign once again. If we live in a universe dominated by the energy of nothing, then the future is bleak. The skies will grow cold, dark, and silent. But the reality may be even harsher. A universe driven by vacuum energy is the worst possible environment for life. Any civilization that arises is destined to vanish, starved of the energy needed to survive. The cosmos will persist, but there will be nothing left to marvel at its vastness. If matter was born from quantum processes, it is also destined to decay through them. Physics is a two-way street. Creation and destruction are mirror images. In the far future, protons and neutrons will disintegrate, atoms will fade, the universe will approach a state of ultimate simplicity and perfect symmetry, mathematically beautiful, but utterly devoid of matter. Some theoretical physicists go further. A universe with positive vacuum energy, they argue, is inherently unstable. Sooner or later, it must collapse or tunnel into a lower energy state. The universe could once again shrink to a point and dissolve back into the quantum fog from which it was born. It will vanish as abruptly as it appeared. And when that happens, the answer to the oldest question, why is there something rather than nothing, may finally be disarmingly simple. It won't last.